Morning Year 10. Well, I won't be in today, but I know some of you worry about missing your fix of mathematics. So, have I got something for you? We're doing graphs of exponential functions today. And we're actually going to add another entry into our list of graphs. So I'll quickly put our gallery together at the moment. So this is our gallery of graphs. And remember we started with, in year 8, y equals x, that one. Then we established a parabola. These are all our basics. Then we've got the inflected cubic, something like that. Okay, not the world's best version of that. Maybe like a quartic, that one there with like the bottom of it's a bit flatter than the parabola. What else do we have in the gallery? We had a circle, y squared equals x squared plus equals r squared. That was that one there. We had a hyperbola. Like so. Remembering that guy had some vertical and horizontal asymptotes as well. So that's our kind of gallery at the moment. I think that covers pretty much all of the ones that we've done. So our new entry today is going to be something like y equals 2 to the x, where our base will be the variable value. Okay, that's what's going to vary here is our base. And given that that's an exponential function, you saw yesterday I drew up an exponential function. They look like that, or that's our basic exponential function. And any base above 1 will produce a graph that looks roughly like this. So let's go ahead and explore what these look like, or why they look like that. And as usual, what we'll do is poke the bear. And so all we'll do is start with a function and go, ooh, how do you behave when I put 0 into you? So you'll notice that both of these functions here have 2 to the 0 or 3 to the 0. So both of them have a y-intercept of 1. All right, what else do we know? This one's going to be 2 to the 1, which is 2. This one's going to be 3 to the 1, which is 3. This is going to be 2 to the 2, which is 4. This is going to be 3 to the 2, which is 9. So the larger the base, the faster the exponential growth. And that should make sense because that's the thing that's growing at an exponential rate. So yeah, the larger the base, the faster the exponential growth. 2 to the negative 1. Well, remember, 2 to the negative 1 by the index law is 1 over 2. Okay, it's the same thing. So this is going to be 1 over 3. And this one's going to be 1 over 2 to the negative 2. 2 to the negative 2. Which is going to be 1 over 2 to the 2, which is a quarter. That one's going to be a quarter. This one is going to be a ninth. Again, for those of you not sure how I'm getting that, y equals 3 to the negative 2, which is the same as 1 over 3 to the 2, which is 1 over 9. Now, just a couple of things. So what you should see is that as x increases, these values here will tend towards infinity. Okay, they'll just get larger and larger and larger. These values over here, what's going to happen is as x tends toward negative infinity, can you see what's going to happen here? So let's just add another entry and go negative, I don't know, 3,000. Well, that's going to be y equals 2 to the negative 3,000, which is y equals 1 over 2 to the 3,000, which is a massive number put into 1, which will go very, very few times. In fact, 0.0000. The fact of the matter is that the smaller this gets, the less times this will go in here, the closer and closer it's going to get to 0. But my question to you is it going to get to 0? And you should see that it's not going to actually make its way to 0, which means that that the 2 to the x function does have an asymptote. All right, so let's graph it. Okay, so we've got y equals 2 to the, let's do 2 to the 0, which was 1, 2 to the 1, which was 2, and 2 to the 2, which was 4. That one was a half and a quarter. All right, so I'll try my best to draw a decent looking exponential curve. Something like that. Okay, and you can see that this is the value it tends toward. So all we do here is we whack in a horizontal asymptote. And remember, the equation of that asymptote is y equals 0. It doesn't have a vertical asymptote, so like the, what do you call it, like the hyperbola, there is no vertical asymptote. It just keeps climbing to positive infinity, a bit like a parabola that doesn't have a vertical asymptote. All right, so just choose a different color, and we'll note that 3 to the x goes through there. 3 to the 1 is 3. 3 to the 3 is 9. So we got this more exponential growth, if that's a word. What was it, a third? So roughly there. And a ninth, so just getting closer down here. So that's our y equals 3 to the x, and this is our y equals 2 to the x. All right, so we've got some different transformations we can do. Now, what's going to happen with this is just like a parabola. So this one here is a reflection in x axes. All right. So what that one's going to look like is it's basically going to be this reflected in the x-axis. So I'll just draw that. So that 1 is going to go to -1. That 3 is going to go to -3. And we're going to get something like this. I'm on fire with the graphs today. They look good. So that's y equals -3 to the x. Okay, this one here, you're going to find that one, and you're going to learn a little bit more about this in 11 methods next year. That there is a reflection in the y-axis. All right. So what that's going to do, and I'll just give you a quick demo. What that's going to do is take a graph, and instead of reflecting it in the x-axis, so if we've got y equals 3 to the x, the standard, 3 to the z. All right, there's our standard y equals 3 to the x there. And if I just put a negative sign in front of the x, you can see that what that does is reflect in the y-axis. So you can reflect in the y, you can reflect in the x-axis, you can actually reflect on pretty much anything on the Cartesian plane if you want, but more on that in 11 methods. At the moment, we just want to know or understand that that's a reflection in the y-axis. So again, I'll change color here to red. When I reflect that in the y-axis, it'll stay in exactly the same spot. That is going to go to there. You can see it's going to be asymptotic. Something like that. Y equals 0. Okay, now this thing here, you need to be aware that that is a dilation factor, and intuition will say that that's factor 2, okay, factor 1/2, but it's actually factor 2 in y axis. All right. This one here is a dilation factor to in x axis. So that should be familiar. That's just like a parabola, I suppose. If it had 2x squared, that's the dilation factor. This one should not be familiar, nor will that be intuitive. Again, we cover that a lot more in methods next year. Okay, so let's do this graph first of all, the dilation factor 2 from the x-axis. What that basically does is it'll take all of the points and multiply them by 2, multiply the values by 2. So this 1 is going to go to 2. And we can test that by just subbing 0 in there, and we can see that that's going to be 3 to the 0, which is 1. 1 times 2 is 2. All right, so we can see that is going to happen. Now this value here, whatever that one is, that should be, that's 3 to the x. 3 to the negative 1 is negative 1/3. So that should go to here, negative, that should be 2/3. And we can try that. Let's just try that. Y equals 2 times 3 to the negative 1, which is 2 times 1 over 3, which is 2/3. So all we're going to do is just double the distance. Okay, and this point here, instead of 3, would be 6. Well, that's what we're going to aim for anyway. So we're going to come up through those points and head towards that one there. That's y equals 2 times 3 to the x. Now what this one does, this one here will dilate it by a factor 2 in the y-axis. Okay. So interestingly, this point here is going to stay exactly the same spot, or in exactly the same spot, because when you dilate the y value of 0 by a factor of 2, it stays in the same spot. But you can also see that, hopefully, that if you sub 0 in here, we can see that that's 3 to the 0, which is 1. Okay. All right, so what we're going to do now is dilate some other values. So this value here, you can see that the distance from here to the y-axis is this. It's just going to double the distance. Okay. This value here, you can see it's a distance of 1. It's going to go to 2. This is a distance of 1 away, so it's going to go to here. This negative 2 is going to go to negative 4, somewhere down here. All right, so let's try and draw this. A bit harder to draw that one. Yeah, okay, that's terrible, but it'll do. Right, so hopefully you can see that that's a dilation factor 2 in the y-axis, but if you can't, just copy it down in your notes just for the moment and sort of hold on to that thought. Okay, here is our last transformation. So this one here was a dilation, this one here was a reflection. Hopefully you can kind of think, oh, I know where this is going. So we'll do this one first because this is a more intuitive transformation, and hopefully you can see that that is a translation 1 unit up. Now when we translate this graph 1 unit up, what's going to happen is the asymptote is also going to move 1 unit up. Right? So the asymptote, which originally was here for the 3 to the x function, is going to go up to here, and everything is going to move up with it. So hopefully you can see that this y value is going to move up 1. This y value is going to move up 1. This value here is going to move up 1, etc., etc. Y equals 3 to the x plus 1. Okay, now what about this graph here? Well, maybe you can see it, maybe you can't. But again, this is something that we cover in 11 methods a lot. So this is a translation 1 unit up. This one here, see if you can think like a parabola and understand what that will do. Okay, and that is a translation 1 unit. and have a punt on where you think this is going. Is this going 1 unit to the left or 1 unit to the right? I bet many of you think this moves 1 unit to the right, but it actually moves 1 unit to the left. And the reason for that is sort of the same reason for a parabola. This is not the best reasoning here, but if I said to you, I've got this parabola that I want to draw, you'll remember or you'll recall that that moves the parabola 2 units to the right and 3 units up. So this is kind of the same as the parabola, where that is the thing that is moving, okay? So what that's going to do is move this blue graph 1 unit to the right. Okay, so this value here is going to go to here. This value here is going to go to roughly here. This one is going to go here. 1 unit to the right. So, hang on a sec. 1 unit to the left. Oh my goodness. Left, left, left. 1 unit to the left. All right, that should be enough to draw. So it suggests that the y-intercept should be 3. Let's just try that. 0 goes in, 3 to the 1 is 1. Okay. So if you're not too sure about why that moves to the left or whatever, you'll still be able to get the x-intercepts and the y-intercepts, and that will help you sketch them. All right, so speaking of, let's sketch some exponential functions. So we've got a y equals 2 to the x, and what's happening is it's being dilated by a factor of 3 from the x-axis. All right, now because it's got no vertical translation, that'll mean that the asymptote is in exactly the same spot. So we know it's going to look like that, but the dilation factor is going to affect the x-axis intercept. And instead of being at 1, it's going to be multiplied by 1, so it's going to be at 3. We can just do this by kind of subbing in 0 to get the y-intercept. So remember, the y-intercept occurs when x is equal to 0. 2 to the 0 is 1, y equals 3. So we're going to pop that there. And then all you need to do to get full marks is sketch something exponential looking. Okay, and that's fine. 0, 3. All right, this one's an interesting one. So this is the standard 2 to the x function moved 4 units down. So I'm going to put in a horizontal asymptote at y equals -4. That's because the standard asymptote, which occurs there, wants to be moved down 4 units. Remember, everything moves down 4 units. Okay, that means that the y-intercept, which was originally at 0, 1, should go to -3. But if you're not sure, just do this. 2 to the x, take 4, and y-intercept occurs when x is equal to 0. So we're going to go 2 to the 0, take away 4, 1 take away 4, -3. So here's -3, -2, -1. Okay, so y-intercept is there. All right, now you can see what's going to happen is it's going to have an x-intercept as well. So we want to know where that x-intercept is. So the x-intercept occurs when y is equal to 0. How do we solve that? Well, we're going to take the 4 over to this side here. And you can think about this intuitively, or you can think about kind of equate the bases. You can see that the x-intercept is going to be 2 when we pair off the bases. Pop it in there. Draw your exponential function. Lovely. Okay, got a couple more to draw. Right, this one here, it's reflected in the x-axis and it's up 1 unit. Let's take care of the translation first. Grab the asymptote, which was at 0, and bring it up to 1. Because it's reflected in the x-axis, what should happen is it's going to go like that. Okay, so it takes the standard it goes up 1 unit, and then it's going to reflect it like so. Okay, so I know that I'm going to get something like this. All right, so all I need to get is the x-intercept and the y-intercept. So let's get the y-intercept first. So occurs when x is equal to 0. Okay, be careful here. This is 2 to the 0, which is 1. 1 gets negated, and it's negative 1. So it suggests that the y-intercept is 0. That also means that the x-intercept is 0. We don't need to find that individually. And we've got everything we need. All right, this one here, we need to look at that and just sort of go, okay, I know that this is going to have a reflection in the y-axis. Hopefully you can see that through intuition. I'll show you another way to do that as we sketch this. Right, so asymptote is moved down 1 unit. Y-intercept occurs when x is equal to 0. So f of 0 is 2 to the 0 take 1, which is 1. So that means negative 1, 1. Okay, yeah, I knew something was going wrong there. Absolute rocket scientist here. 2 to the 0 is 1. 1 take away 1. No one is to hear of this. 1 take away 1 is in fact 0. All right. Now, typically we'd then draw it like this. Okay. We need to understand what's happening here. Okay. And what's going to happen is that the graph actually goes like this. And if you're unsure, again, what we'll do is just poke the bear a little bit. So what we'll do is try to jam in a negative value. Let's just say negative 100. Okay. Now, hopefully you can see that when we do f of negative 100, that's going to be 2 to the negation of 100, which is 2 to the 100 take away 1. That's a massive number. So this side's the high side. Let's just test whether this is indeed the low side. Okay, so we'll do f of 100, say. And now you can see that when we put 100 in, we're going to get 2 to the negative 100 take away 1, which is 1 over 2 to the 100 take away 1. This value here is excruciatingly small. 1 over 2 to the 100 is a massive number. 2 to the 100 is a massive number. So that's almost 0 times. And 0 take away 1 will leave us somewhere down here somewhere. So hopefully you can see that that is indeed a reflection in the y-axis. All right. So there's a few graphs. Okay. What I'm going to get you to do now is to practice sketching on your own. The questions I'm going to get you to do are these ones here, 3F. All right. So use the opportunity to get some work done, and I'll catch you guys later on in the week.